We finished off talking about every single kind of simple potential that we could solve for the Schrödinger equation, the time-independent Schrödinger equation. But notice something. For the Schrödinger equation that we've been covering so far, everything is a scalar. Sure, technically, we take in vector inputs, but our force has been a scalar. Our potential, well, actually, potential doesn't change, so potential is still a scalar. But our wave function, still a scalar. And that's not how it's going to look soon. In real life, things are vectors. You probably already know that. So, how do we talk about vectors in quantum mechanics? What's the formalism behind them? Well, it all comes down to something that we call bracket notation or bracket notation. I'm not exactly sure how to pronounce it, invented by Paul Dirac. Now, this is an extremely interesting notation. Well, it's not actually that interesting, but there are two different kinds of notations for vectors, bra and ket. They're not actually notations, they're more like operators that work on a regular vector. So how do we use them in the context of the Schrödinger equation? How do we extend the one-dimensional Schrödinger equation to 2 dimensions or 3 dimensions, like the world that we actually live in? Well, that's what we'll be beginning to look at in today's quantum mechanics lecture. Thanks everyone